So as Sharon said, I'll talk, we started this project almost at the same time of starting the Peer Bridge program. It is the for Bridge Rapid Assessment Center for Extreme Events. And the objective is to develop a data and simulation framework for real-time rapid and near real-time comprehensive assessments of Caltrans bridges. And then based on this assessment, BRACE 2 will provide recommendation about the operation of bridges to Caltrans engineers after an earthquake event. So the idea is we make use of the accelerometers that are already on the different bridges so we can learn about the condition of the bridge following an earthquake event. So the centerpiece of the BRACE 2 is the decision-making platform, which reside on a cloud server eventually, which is a set of Python scripts that uses the data from sensors on the bridges. We have a specific bridge that is the main bridge we are focusing on, which is Hayward Bridge. I'll talk about that when I talk about the bridges we are considering. And we obtain the data from the sensors on the superstructure and also from the geotech array. And the sensor data is obtained through collaboration with California Geological Survey, where the data is processed, and we receive both raw data and processed data in real time. The bridges are modeled through their components, so we can determine the limit states of the different components. And by comparing the computed demand to the limit states, we can make a real-time rapid assessment and provide the recommendation for that. If we want to do a more detailed modeling involving the global bridge model, which is ready for model updating using either conventional optimization to adjust the model parameters or using machine learning as part of this decision-making platform, then we can provide a more comprehensive assessment of the bridge response, but this will take some time, so that's why it's provided in almost real time or near real time in terms of obtaining the bridge conditions. So to elaborate a little bit on each of these two types of assessment, both uses the raw or the processed acceleration data. So in the real-time assessment, we estimate the EDPs, the engineering demand parameters, for example, drift ratio, and knowing the bounds of the different component limit states, we see where this EDP reside between, let's say, limit state I and limit state I+1. Then we can do assessment of the component damage, which could be a column or the pile foundation. And based on the different component damage states, we can assess the bridge damage condition, and then we provide the recommended action. On the other hand, for the near real time, the main feature that is added is the global bridge model that is used in conjunction with the data to perform nonlinear dynamic analysis of the bridge model, and then a combination of physics-based and data-driven or a hybrid method we can use to assess the bridge damage condition. And again, we provide the recommended action. But because of the utilization of the global bridge model, not just comparing predetermined limit states to the demand, here we involve the nonlinear dynamic analysis, which delays the time for making a recommendation. That's why it's near real time. At the moment, we're focusing on 5 bridges. One bridge is used for real-time monitoring, the Hayward Highway 580-238 interchange. And the other 4 bridges, we just use them with the historical CSMIP data. So these other 4 bridges are not, we do not receive the data in real time. So this is just to limit the scope of the work. For this number 1 bridge here is monitored in real time, but the other 4, we mainly use data that's available in the CSMIP database. These 5 bridges, they span different bridge systems. They span different bridges with different number of already recorded earthquake motions, and also they span bridges of different number of sensors, from 6 sensors that are available all the way to 34 sensors. They are also, these 5 bridges are geographically distributed over the state of California, so they give us good coverage of the seismic hazard all over California. And I put arrow here next to the Hayward Highway bridge because it is our main bridge that all steps of the BRACE 2 are being exercised, including acquiring the data in real time. The team working on BRACE 2 is divided into 4 working groups. Working group 1 focus on the global bridge modeling. Working group 2 focus on the component modeling and determining the limit states of the different bridge components. Working group 3 focus on sensors and data processing. And finally, working group 4 focus on hardware and the cloud computing infrastructure. The sensor data streaming is a collaborative work between PEER and CGS, where CGS has access to PEER server. They established automatic login process, and they upload raw and process data in real time. So this is an example of how much time it takes for the data transfer duration, which is the time difference between the end of recording and when PEER server receives the data. And in a recent small earthquake that happened near Berkeley, it took about 1 minute for the data to be acquired. And if we get the process data compared to the raw data, this has a small overhead of about additional 5 to 6 seconds. So it's not that much difference in terms of the time at which we receive the data if we use the process data compared to the raw data. So just to show you a couple of quick results, this is from the Hayward Bridge using historical data. This is before BRACE 2 work started. This is back in January 2018. There was this small earthquake that happened, and this is what we get as for transfer function, which tells us this bridge has a natural period of about 1.14 seconds and damping of about 6%. This is the same bridge using real-time acquired data for the event that happened last June, end of last June. And this data was received by CGS within 1 minute or so of the event, as I mentioned before. And again, from the transfer function, we see that we are getting pretty much the same response. Both events are small events, so no damage is expected. So having the same dynamic response is the case. So as far as global modeling and model updating, So we are now working on finishing up the model development for all 5 bridges, which include model completion, gravity analysis, eigenanalysis, and dynamic analysis. The main part that's remaining is pile soil foundation structure interaction modeling that's still ongoing. Also in the bridge global modeling, we have a couple of major tasks that are in progress. Model updating using conventional optimization algorithm and model updating with machine learning enhanced optimization. So these are still work in progress. So the Hayward Bridge global model, just to tell you what goes under this major task. Our focus is to do open seas modeling, even though we do modeling in other platforms as well, which include modeling the columns, the cap beam and the bridge deck, the in-span hinges, abutments, soil structure interaction, and damping. Most of these tasks are completed with the exception of the soil structure interaction that's still work in progress. Here is some results from the Hayward Bridge global modeling in terms of eigensolution for the mode shapes in the longitudinal, transverse, and torsional response, and comparing the computations in the middle column of this table here to those that are identified from the data. It's pretty reasonable with the exception of the transverse direction that is still will be improved once we complete the modeling aspects of the boundary condition. How much time do I still have?
2 minutes.
Okay, so I'll go a little faster here. So again, for the dynamic response, we have a reasonable comparison in the longitudinal direction. The transverse direction still needs some improvement. As far as the optimization algorithm, the conventional approach is to use some response quantity like the period that will be replaced by the identified, let's say, peak acceleration. And by making sure the weighted error between computed and identified is minimized, we can adjust the different model parameters. We're working in acquiring data in terms of the involved uncertainties for the different parameters, so we can constrain the optimization algorithm for these parameters to be within mean plus or minus twice standard deviation. As far as the procedure for computation of the limit states, we did some work in validating OpenSea's model using platforms like Abacus. Because of the intensity of computation in Abacus to do a full bridge, so we do that for a single column or a single bend. And once we have confidence in the OpenSea's model, then we can use OpenSea's for cyclic analysis so we can determine the different limit states. We mainly use stream-based limit states based on the work that was done by Georgia Tech and the RISE team, and also Cliff Robley in G2F. And this was presented through the work of Sashi Kunath, who led a peer workshop. And we use the same 7 limit states. They have a good representation in terms of strain values, and we have specific values for the Hayward Bridge we are studying. Just to quickly show you result of another bridge, the Lake Crowley Bridge. So here is a comparison between Abacus and OpenSea's. And the focus is mainly in achieving comparable limit states, which are marked here. There are definitely some differences because of the detailed nature of the 3D model in OpenSea's compared with a simplified model in, detailed model in Abacus compared to the simplified model in OpenSea's. My last slide here, just to give you the big picture. So we are finalizing a script for automated processing of the CGS data, where this script basically will identify when new data has arrived in a form of a zip file. We unzip the file, we extract the acceleration, velocity, and displacement for each channel, and develop a summary file. And then we extract the accelerations from the channel at the base of the columns, transform them in the XY axes of the OpenSeas model, so we can perform dynamic analysis using this input motion. Then we can compute the drift ratio of the columns where sensor data are available, and then we can make a primary comparison of the drift demands and the pre-computed limit states. So this will be part of the decision-making platform. So this script is being finalized now in conjunction with the data stream from CGS. And with that, I will stop.